regarding the privacy of label-only access to neural network classifiers via iDP verification. Okay, so neural networks are very successful but also prone to privacy leakage attacks. In privacy leakage attacks, the attacker extracts sensitive information about the training set. For example, the membership inference attack, at which the attacker tried to infer if an item was part of the training set or not. Other attack is the reconstruction attack, where the attacker tried to reconstruct an item from the training set. Okay, so to cope with these attacks, differential privacy was employed. In differential privacy, it's a popular criteria which addresses the question of how to analyze data while preserving privacy. Typically, we have a data analyst which can access a data set using a mechanism A. And differential privacy says that to make A private, we should add randomness. Formally, A satisfies epsilon differential privacy if for all dataset D and D tag differing in one element, the probability to get an output O by applying A on D is similar to the probability to get an output O by applying A on D tag. This means that one item should not change the output of A. Now, differential privacy was employed in neural networks using DPSGD, and the idea was in the training itself, we want to add noise to the weights and biases to make the network private. The problem with that is that could degrade the classifier utility significantly. And now we ask the question, how can we preserve privacy while maintaining utility? This brings us to iDP, individual differential privacy. It's a property that was proposed by Jordi Soria. It suggests a balance between privacy and utility. It maintains the same structure as differential privacy, and it considers a given data set such that it provides privacy guarantees only for a given data set. In contrast to differential privacy that provides guarantee over any data set, here we focus on a given data set, and it's suitable to neural networks because in neural networks we have a given data set. Okay, so formally, given a data set D, a mechanism A is epsilon iDP if for each data set D tag that differs from D by a single item, the probability to get an output O by applying A on D is similar to the probability to get an output O by applying A on D tag. D is given, D tag differ by one item, and we do not expect one item to change the output of the mechanism A if it's private. Okay, so how can we apply iDP in neural networks? This brings us to our goal. We want to develop an iDP mechanism to preserve privacy and to maintain the classifier utility. Before that, let's try to understand how we can apply iDP in neural networks. So in neural networks, we have a training set D, we have a training algorithm A, and we can train a classifier, for example, this orange classifier, using the full training set. Similarly, we can do another training set, D tag, which have the whole training set of D except from one item, the first item, and train the blue classifier. After that, we can compare the results of the orange classifier with the blue classifier. If the results are similar, this means that the orange classifier do not remember a lot about the first item. He saw the first item, but he still classifies like classifier that does not saw the first item. If they are significantly different, this means that it remembers a lot about the first item and can leak privacy. So this way, we can preserve privacy. We do that for the other item, the third item, the fourth item, and compare outputs. Okay, so how we can implement that? Here I present two naive approaches. We can go for brute force approach. We have the classifier that was trained using the whole training set. We have classifiers that were trained using missing one training item. And each time we have an inference and X, we can pass it through all the classifiers, check outputs, compare them, and if there's difference, we can add noise to make the mechanism private. Another option is to adapt DPSGD to iDP. This means that in the training itself, we can add noise which is proportional to iDP, and to get privacy like that. The problem with the first option is high inference time. Each time we have an input, we now should pass it through many classifiers and not practical. The problem with the second approach is it will add eventually a lot of noise and affect the utility of our classifier. And now we ask the following question. Can we design an iDP preserving approach that minimizes inference time and noise? And this brings us to our key observation. We observe that individual privacy leaks via inferences, but not all the inferences. And to understand that, let's consider the classifier here, the blue one. Each time we have an inference X, actually what we do, we access the weights and the biases of the network. But the weights of the biases are functions of the training set. So each time we access the network, we actually access the training set. But the question if all x's can leak privacy about the training set. So to understand that, let's consider the figure here. We have classification results of a classifier, a 2D classifier, classifying into two classes, class 0 and class 1, and we show the decision boundary as the black line in the middle. We add to this all the classification, the decision boundaries of other networks that were trained using the same training set except from one item, and show them in colored lines. And now let's consider the green input here, the X. If we look at it, it is classified similarly over all the classifiers. It means that this input, this access, is non-leaking. We should not add noise to it to preserve privacy. If we look at the white one, sometimes it classifies as 0, sometimes it classifies as 1. This input is leaking, and we should add noise when we classify it. So our idea is to define a bound. This bound starts from the decision boundaries of the classifier, the black classifiers, expand, and its goal is to bound all the leaking inputs. So eventually, each time we have a leaking input, we add noise. Each time we have a non-leaking input, we do not need to add noise. This way we preserve privacy and we preserve utility. Okay, so we said that we want to define a bound starting from the decision boundaries. How we can do that? We use the well-known term of classification confidence. In classification, we have typically an input X. We show it to the classifier. At the output, we have classification scores. Classification confidence says if X is classified as C, then the confidence is the score of X minus the score of the maximal other label. To visualize this, let's consider the figure here. At axis Z, we plot the classification confidence. At axis X and Y, we plot the input domain. We can see that at the decision boundaries, the confidence is 0, because at the decision boundaries, we do not classify. So our bound will start from confidence 0 and expand such that it captures the leaking inputs around the decision boundaries. Okay, so so this is how it will looks, our bound looks, and now let's define our property using the classification confidence. We say that we want to find the maximal classification confidence at which we could find a leaking input. This means the network that was trained using the full data set will classify to C, but at least one other network which was classified using the full data set except from one item will classify otherwise. And here, this is how we write our property. Okay, so now we define our property, and now let's see how we compute it. To compute it, we depend on formal verification, especially in MEAL, mixed integer linear programming. And we have our property here. We should encode it as MEAL. Now, here we can find our classification confidences for each network. This means that for each classification confidence, we should encode the full network. So we will eventually encode a lot of networks here as large as the training set size plus 1. And that would be problematic in MEAL, because MEAL assigns one continuous variable and one Boolean per neuron. Here we have a lot of neurons in our probability, and MEAL complexity is exponential in the number of Boolean variables. So a straightforward MEAL encoding is impractical. How we address that? Naively, we can, instead of encoding all the network as a single MEAL, we can compute a bound for each network. This means that we can compare at each time two networks, the original network who shows all the training set with one network who saw all the training set except from one, and compute a bound. We can do that for the first, for the second, for the third, for the fourth, compute bounds, and at the end get the largest bound because it bounds all the other bounds. This way, we reduce the Boolean numbers from a lot of networks into two networks. But also this approach is impractical because we will end up solving a lot of MEAL problems, as many as the size of the training set. And this way, it will take us a lot of time. So what we do, we propose to do hybrid networks combined with branch and bound. This is our solution. Okay. So now let's try to understand what do we mean by hybrid network. We say that instead of go and compare pair, we can go for all the blue networks here that was trained using the whole training set except from one item, and merge them into one hybrid network. Now the hybrid network defined by intervals. Each interval bounds the values of all the original networks. For example, we can look at the bias here. It goes from 0 to 0.3. And if we look at the biases in the original network, we have 0, 1, 0, 0, 1, 0, 3, so we bound all the values. And then what we just need to do is to compare the hybrid network with the original network, the orange one. We will get our bound, and we can see that the bound that we get is a little bit larger than the bound that we get when we solve precisely. And why is that? Because in hybrid network, because we are working with intervals, we add overapproximation. For example, in this interval 0, 0, 3, we have a value of 0.2, of 0.2. But there is no bias in the original network with 0.2. So intervals does overapproximation, and because of this overapproximation, we get a sound but not precise bound. So what we do is branch and bound. We can go for the hybrid network and split it into smaller hybrid networks, and this goes on and on until we reach a precise bound. Okay. So now let's describe our approach. We call it LUCID. It accepts all the classifiers. We start from doing the hybrid network. We encode as meal. We submit the encoding to a solver, and the solver compute a bound. It retrieves a bound. We stick this bound with its hybrid network and push that into priority queue. Now after that, we can fetch the hybrid network with the maximal bound and check if its size is 1. If its size is 1, then we finish, because we have a bound, a hybrid network composed from network which can bound the rest. And then we could finish. Otherwise, we split it into smaller hybrid network and do other iteration. In inference, each time we have an X, we can compute its confidence and compare it to the bound. If it's smaller than the bound, then it's leaking. We should add noise. If it's larger than the bound, then it's not leaking. We do not need to add noise, and we can retrieve the classification as it. This way, we save privacy and we save utility. Okay, so now let's talk about our evaluation. We evaluate LUCID on several data sets. We compare it to naive approach and DB-SGD based approach. It achieves an inference time that is 156,000 times faster than the naive iDP. Its accuracy is 27x less degradation compared to the naive noise. If we compare it to the DB-SGD approach, it achieves 0 iDP with only 1.4 accuracy degradation. DB-SGD approach cannot reach 0 iDP, and it can reach 1.2 degradation compared to 12.7, which DB-SGD achieves. Of course, we pay in time. To compute the bounds, we need 4.8 hours, and to train a network for DB-SGD, we need less than a minute. Okay, so now let's summarize. We address the problem of privacy leakage in neural network classifiers. We develop an iDP mechanism. We introduce the new concept of iDP-DB bound. We propose LUCID, which compute this bound and solve the privacy leakage. LUCID relies on meal, hybrid networks, and branch and bound techniques. It achieves better results when it compared to DB-SGD approach and naive approach. So thank you for your attention and questions.
Any question? Please come up. And next speaker, please come. Yes, thank you. So yeah, while we are switching the gear. Oops, watch out. So you mentioned this, degradation in the precision.
Yeah.
Right. So it depends on the applications, right?
It depends on what?
Oh, so something was with 27 times less precise, and the other was like 0 point something.
Yeah.
What makes that difference, you think?
The idea at the end is to keep the classification utility, the classifier utility, but the time is in computing the bounds, because it takes us time to compute the bounds. But that's what we do once and offline. Once we have the bounds, we can use them for any input. So there is a trade-off here. For example, the SGD do not need to compute offline bounds, they need to train a network. We do not train a network, we compute bounds.
Okay, thank you.
Thank you.